For 30 days, the map was blank. Then, overnight, a tight cluster of earthquakes appeared on a long fault off the central California coast that almost nobody watches. The largest was a magnitude 2.1 nothing you'd ever feel. But the jump from nothing to something is exactly the kind of signal seismologists don't ignore. Tonight, you'll learn why a fault's silence can be more dangerous than its noise, and which silent giants around the Pacific have scientists genuinely worried. Sometime overnight this weekend, just off the coast of central California, a small knot of earthquakes appeared on a map where there had been nothing at all. The two largest were a magnitude 2.2 and a magnitude 2.1, with a handful of smaller shocks clustered tightly around them. If you live anywhere near the central California coast, you did not feel these. Almost nobody did. A magnitude 2 is the kind of event that a sensitive instrument records and a human being sleeps right through. By every ordinary measure, these quakes are nothing. And yet seismologists who watch this part of the world stopped and looked twice because of where they happened and when. They happened on the San Gregorio fault, a long offshore fault running through the Big Sur and Point Sur region, the stretch of coast people simply call the Sur. The San Gregorio is not a household name. It is not the San Andreas. It rarely produces anything large enough to make the news, and it is so far down the list of things people monitor that it is left off some of the dedicated regional fault listings entirely. For the previous 30 days, the catalog for that fault was blank. No quakes. Nothing. And then, against that completely empty background, a tight little cluster lit up. That contrast is the entire reason we are talking about it. The events themselves are unremarkable. The change is what matters, going from zero to a cluster on a fault that had been silent for a month. The people watching this in near real time were careful, and they were honest. They said plainly that there was definitely nothing big happening. But they also said the thing that makes this worth your time tonight, which is that the places that suddenly start showing activity after a long silence are exactly the places worth watching. So, here is the question that drives everything that follows. And notice that it is a question, not a prediction. When a fault that has been quiet for a long time suddenly produces a small cluster of earthquakes, is that just noise, the random background hum of a restless planet? Or is it the first hint that stress along the plate boundary has built to the point where the smaller faults are finally starting to give? Those are very different answers. Tonight, we are going to walk through how scientists actually tell them apart, and why the most dangerous answer is not the loud one. You have to understand what these instruments are actually seeing before any of this makes sense. The California coast is not a quiet place. It is one of the most heavily monitored pieces of ground on Earth, threaded with seismometers that pick up thousands of tiny tremors a year, the overwhelming majority of which nobody ever notices. Two magnitude 2 events, in isolation, would never rate a second look. They are statistical background. The reason these did is the same reason a single cough sounds loud in a silent room. It was the silence around them that made them register. The San Gregorio is a real fault, not a minor crack. It is a long, structurally significant offshore strike-slip fault, part of the same broad plate boundary system that includes the faults California genuinely fears. It runs underwater along the central coast, which is part of why it gets so little routine attention. There are no neighborhoods sitting directly on top of an offshore fault, no daily reminder that it is there. Out of sight, and for 30 days, out of the catalog entirely. So when a cluster appeared on it, the appearance itself carried information, even though each individual quake did not. The same night, by the way, the rest of California behaved exactly as you would expect. A couple of small quakes near Riverside on the San Jacinto fault zone, none above magnitude 2.5. Some scattered shocks in the Coast Range faults of Northern California. The Cascadia margin to the north was quiet, which lined up neatly with another reading from that night. The slow slip and tremor map under the central Oregon coast showed only about 10 epicenters, a low number. When slow slip runs low up there, the shallow crustal quakes onshore tend to stay quiet too, and that is precisely what the map showed. Everything fit, everything except that little offshore cluster, sitting where the map had been empty. This is the part that trips people up, so let me be very clear about it. The strangeness here is not the size of the quakes, it is the statistics. It is the jump from nothing to something on a fault that does not light up often. That jump is the only signal-shaped thing in the entire picture, and on its own, it is a very weak signal. It is enough to make a careful scientist raise an eyebrow and add the San Gregorio to the watch list. It is nowhere near enough to make anyone issue a warning. And the gap between those two things, raising an eyebrow and sounding an alarm, is where almost everyone gets earthquakes wrong. Here is the idea that turns this whole story inside out. In most of life, quiet is reassuring. A quiet engine is a healthy engine. A quiet patient is a comfortable patient. But in earthquake country, quiet is not the same as safe. On a major fault, long silence is not the absence of danger. It can be the measure of it. To see why, you have to picture what a fault is actually doing while it sits there doing nothing. The tectonic plates that make up Earth's surface are always moving, slowly, at about the speed your fingernails grow a few centimeters a year. Where two plates meet along a fault, that motion does not politely stop. Most of the time, the two sides are locked together by friction, stuck fast. But the plates behind them keep moving anyway. So the rock on either side of that lock patch begins to bend and store energy like a spring being slowly wound, or a stick you are bending a little further every year. The fault holds, and holds, and holds, until the stress finally exceeds the friction holding it shut, and the whole thing releases at once, snapping back in seconds and turning decades or centuries of stored motion into an earthquake. Now sit with what that means. A locked fault that has not moved in a long time is not resting. It is loading. Every quiet year is another year of strain wound into the rock. Another year of energy that has gone in and not come back out. The silence is not telling you the danger has passed. The silence is telling you how long the spring has been winding. This is the inversion at the center of tonight's story. And it is why seismologists do not breathe easier when a major fault goes quiet. They watch it more closely. That is also why those small California quakes pointed at something bigger than themselves. On their own, almost certainly nothing. But they are a reminder, a small flag planted on the idea that the quiet stretches of a plate boundary are the ones storing the most. The cluster is the doorway. What it opens onto is the real subject, not the noisy faults that release their stress in frequent small jolts, but the silent ones that have been holding it all in. Because the faults that frighten the people who study them are not the ones making noise tonight. They are the ones that have made no noise in a very, very long time. Scientists have a name for these dangerous, quiet stretches. They call them seismic gaps. A seismic gap is a segment of an active plate boundary that has not ruptured recently, even though the segments around it have. On a map of past earthquakes, it shows up as a hole, a blank space sitting between zones that fire regularly. And the logic is exactly the inversion we just walked through. If the boundary as a whole is moving, and one stretch of it has stayed locked while its neighbors let go, then that locked stretch has been quietly accumulating strain the entire time. The gap is where the stored energy is highest. The gap is where the stakes are. I want to be careful and honest here, because this idea can be pushed too far. The seismic gap concept is real and useful, but its track record as a precise prediction tool is genuinely debated among scientists. A well-known critique published in 1991 by Kagan and Jackson looked at how the simple gap model had actually performed as a forecaster, and found it performed poorly. Gaps did not reliably break when the model said they should. So the responsible version of this idea is not gaps tell you when, it is gaps tell you where. They identify the segments carrying the most risk over the long run. They do not and cannot hand you a date. Hold on to that distinction, because it is the difference between science and doom-mongering, and we are going to come back to it. The honest statement is that a seismic gap is a place where, when the silence finally breaks, it tends to break big, because there is more stored energy waiting there than anywhere else on the boundary. That is a statement about consequences and about long-term odds. It is not a countdown clock. And this is where the small, almost invisible cluster off California connects to something genuinely enormous. The San Gregorio quakes are a local, present-day example of the pattern, a quiet fault twitching. But the same pattern, scaled up, describes some of the most dangerous places on the planet, where the silence has lasted not 30 days but 100 years, or 300, and where the fault that finally moves will not be felt by a few instruments. It will be felt by entire nations. Those are the silent giants, and there are several of them. And right now, their clocks are running. Start in the far North Pacific, along the Aleutian Trench off Alaska, one of the fastest converging plate boundaries on Earth. There is a stretch of it that some observers describe as a place where large earthquakes simply do not happen because it has been quiet through the entire modern instrumental era. But the historical record for that exact same segment tells a different story. It includes earthquakes of magnitude 7.9, 7.7, 7.6, 7.3, and 7.1, plus a long list of magnitude 6 events, and as recently as 2017, an event near magnitude 7.7. That stretch is not incapable. It is loaded and quiet. The 1946 Aleutian earthquake on that same arc launched a tsunami that crossed the entire Pacific and killed people in Hawaii. The modern quiet is not safety. It is a gap. Move to Japan, and you find the Nankai Trough, a subduction zone fully capable of a magnitude 9 earthquake. Nankai has a long, well-documented habit of producing great earthquakes roughly every 100 to 200 years, often in closely spaced pairs. The last one struck in 1944 and 1946. That puts the trough now approaching 100 years of accumulating strain, sitting near the long end of its own interval. The Japanese government's own assessment places the probability of a major Nankai earthquake in the next 30 years at roughly 70 to 80%. That is not a fringe estimate. That is the official number for a zone with tens of millions of people living in its shadow. Then there is New Zealand's Alpine fault, which runs up the spine of the South Island and is so straight and so active you can trace it from space. It is capable of about a magnitude 7.5. It ruptures on average every 291 years, and the last time it broke was 17 more than 3 centuries ago. A 2021 study estimated something close to a 75% chance of a major rupture within the next 50 years, which makes the Alpine fault one of the most predictable major faults on the planet. And closer to home, the Cascadia subduction zone off the Pacific Northwest has been locked since the 26th of January, 1700, when it last let go with roughly a magnitude 9. That is about 325 years of silence on a fault that has produced more than 40 great earthquakes over the last 10,000 years. 4 silent giants, 4 clocks, all of them running. At this point, a very reasonable thought occurs to a lot of people, and it is worth taking seriously. If small earthquakes release energy, then surely all these little quakes, the California cluster, the constant background hum, are slowly bleeding off the pressure, relieving the big faults a little at a time. It feels intuitive. It is also completely wrong, and the reason why is one of the most important numbers in all of earthquake science. Earthquake energy does not climb in a straight line with magnitude. It climbs explosively. Each full step up the magnitude scale represents about 31.5 times more energy released. So a magnitude 5 is not a little bigger than a magnitude 4. It is roughly 31 times bigger. Go up 3 full steps, from a 4 to a 7, and you are talking about something like 31,000 times the energy. Push it to a magnitude 7.5, and the gap from a magnitude 4 becomes staggering. It would take on the order of 178,000 magnitude 4 earthquakes to release the same energy as a single magnitude 7.5. Let that number sink in. 178,000. To drain one great earthquake's worth of stored energy through small quakes, you would need a swarm of small events so enormous, so relentless, that it would itself be one of the most extraordinary seismic sequences in recorded history, and even then, you would only have matched a single large rupture. The small quakes are not emptying the tank. They are not even making a dent in it. They nibble at the very edges, while the locked patch, the part that actually matters, keeps right on loading. So when you see a cluster of magnitude 2s off California and feel a flicker of reassurance that the fault is letting off steam, that instinct has it exactly backwards. The small quakes change essentially nothing about the great fault's stored energy. The spring is still winding. Whenever a story like this surfaces, a wave of other explanations comes with it, and an honest report has to deal with them directly rather than pretend they are not out there. The same night those California quakes appeared, there was a modest solar flare, a magnitude M1.3, from a sunspot region on the edge of the sun, and another active region growing more magnetically complex. Within hours, you can reliably expect someone to connect the dots and claim the sun is triggering earthquakes. The energy budget alone destroys the idea. Even strong solar activity deposits orders of magnitude less energy into the upper atmosphere than the strain energy locked inside a single moderate earthquake. And there is no demonstrated physical pathway connecting the ionosphere, about 100 kilometers overhead, to brittle rock failing tens of kilometers underground. The careful studies that have looked for a solar earthquake link find, at most, weak correlations that you could never act on. The same physics dispatches the HARP claim the notion that some facility is engineering these quakes. The energy required to move a fault dwarfs anything human technology can produce by something like 15 orders of magnitude, and the geometry makes it worse, since atmospheric heating happens far above the ground while ruptures begin far below it. Nothing bridges that gap. There is no dial to turn. Then there is the cover-up instinct, the idea that the agencies are hiding the real activity, often pointing to the fact that different earthquake catalogs report slightly different numbers, that one feed showed a magnitude 5.2 and another a 5.3, that a quake seemed missing from one list. That discrepancy is real, and it is also the most ordinary thing in the world. Different seismic networks use different instruments, different detection thresholds, and different review queues, especially overnight and for events on the far side of the planet. The data being openly cross-checkable across multiple independent networks is itself the strongest evidence against any cover-up. And one last correction worth making, because it has been circulating. The developing El Niño is not, as some are saying, historic or record-breaking. The actual ocean measurement sits right around plus 0.48, which is technically neutral and only just beginning to warm. A wet California winter is possible if it strengthens. It is a forecast, not a record. So where does that leave the strange little cluster off the California coast? Almost certainly, it leaves it as nothing, 2 magnitude, 2 quakes on a long fault, the kind of background event that happens and is followed by silence again. The most likely reading, by a wide margin, is that this is routine, and that the 30-day blank before it was partly just an artifact of how rarely anyone looks at that particular offshore segment. That is the honest base rate, and it should be the first thing anyone says. But here is what the cluster is genuinely good for, and it is not prediction. It is a reminder of the inversion we have been circling all night. The danger on a fault is not measured by how much noise it is making. It is measured by how much it has stored, and the faults that have stored the most are very often the ones making no noise at all. The Aleutian segment that supposedly never breaks. The Nankai Trough counting toward its 100th quiet year. The Alpine fault 3 centuries past its last rupture. The Cascadia coast locked since 1700. We can read the strain in those places. We can map the gaps. We can state the odds across a decade or a lifetime. The one thing we cannot do, and the one thing every honest scientist will tell you, is turn any of that into a date. That is the uncomfortable truth you are left holding, and learning to hold it is the entire point. The warning is real, and the timing is unknowable, both at the same time. So you do not panic over a cluster of magnitude 2s, because panic over the small stuff is almost always misplaced. But you also do not let a long silence lull you, because on the great faults, silence is not the sound of safety. It is the sound of a spring still winding. Watch the quiet places. We will be tracking the San Gregorio and the gaps around the Pacific as this develops, and we will tell you the moment any of it actually changes.